Surface forces often tend to shape liquid surfaces with rounded profiles, while gravity makes liquid thin and flow, as we know. These two actions generally contradict each other, but capillary action implies surfaces, while gravity acts on volumes. Hence, a natural length scale arises, above which gravity effects are dominant, and below which capillarity reigns. This distance is called the capillary length. Varying the size of drops on a given solid allows us to evidence the capillary length. Here, we deposit drops of water, dyed in blue, on a material that repels water and choose to vary in large range the volume of these drops. The solid, liquid and air being given, all these drops meet their substrate with the same contact angle. However, the global shape is influenced by the volume of water. Small drops are quasi-spherical, while big ones are flattened in puddles. The transition between these two kinds of shapes, sphere and puddles, occurs when the drop radius is a few millimeters, which provides the order of magnitude of the capillary length. The question I want to discuss with you is the shape of a drop when we deposit it on a surface. So the question is, do we see a sphere or a puddle? To address this question, we start from the following situation, where we have the drop on the surface, and we are going to evaluate the two types of energy that it encounters. So we have first a surface energy, which goes like surface tension time R square, so the surface of the drop. And the second type of energy related to the fact that the drop is under the action of gravity, so we call it Eg, which goes to scale like the mass of the drop, so rho r cube time gravity time the size of the drop. And so what you see here is that one type of energy goes like r square, whereas the other one goes like r to the 4. So if we now look at the evolution of these energies as a function of the drop radius, you're going to find a quadratic evolution for E sigma, whereas Eg is going to evolve like the quadratic power, so like r to the 4, whereas this one goes like r to the 2. And what you see on this plot is that these two energy crosses for a well-defined length scale, LC, that writes square root of gamma divided by the density times gravity. So now we have two regions that are separated by LC. The first one is when the drop has a radius smaller than the capillary length. And in this region, what you see is that blue is over pink, which means that the energy related to the capillarity is larger than the energy related to gravity. And so in this case, when E sigma is larger than Eg, we do not expect the flattening of gravity, and we expect to observe only sphere. On the other region, when the radius becomes larger than the capillary length, then it is the opposite. So the pink is over the blue, and so we expect gravity to dominate capillarity, and then the flattening of gravity should take the lead in front of the sphericity imposed by the minimization of the surface. And so now we have answered the question sphere or puddle. So the answer is it depends on the size of the drop with respect to the capillary length. For drops smaller than the capillary length, we will observe sphere, whereas for drops larger than the capillary length, we will observe puddles. So the last comment on this question is about the order of magnitude of the capillary length LC. So LC writes like the square root of gamma divided by rho g. And now if we put numbers, what we see is that gamma for water is of the order of 10 to the minus 2 Newton per meter. We have density of water that goes like 10 to the 3 kilos per cubic meters. And we have gravity, which is of the order of 9.8 meter per second square. So if you put this value in the capillary length, what you get is that LC is of the order of 3 millimeters. And so the conclusion is that for drop size smaller than 3 millimeters, you will observe sphere, and for drop size larger than 3 millimeters, you will observe puddles. It is interesting to realize that even at large scale, where gravity dominates, the wetting conditions still play a key role in the shape of puddles. If we place 2 cubic centimeters of liquid on solid with different wetting conditions, we observe that the puddles select different thicknesses. The larger the contact angle, the thicker the puddle, and the smaller its radial extension. At such scale, drops are flattened by gravity, but they still need to meet the substrate with a well-defined angle, which deforms the puddle edges and forces the liquid to rise when the contact angle is large. The question I want to address is why are puddles sensitive to wetting, despite the fact that they are dominated by gravity? So our question is, why are puddles sensitive to wetting? To address this question, I start from the following drawing, where I deposit a puddle on a solid surface. This puddle is characterized by the contact angle theta, by its radial extension r, and by the thickness h. The volume of this puddle is approximately pi times r squared times h. And the two energies that characterize this puddle are the surface energy, E sigma, that goes like pi r squared times gamma solid liquid associated to the lower interface, minus gamma solid vapor, because this has been removed when we have deposited the liquid, plus gamma for the upper surface. And we neglect the surfaces associated to the edges, which are smaller. This surface energy can be rewritten using the volume as omega divided by h, and this term, according to a Young equation, can be written gamma 1 minus cosine theta. This is the expression of surface energy. Now we move to the expression of the energy associated to gravity. And so we have Eg, which is going to scale like the mass of the puddle, so density times omega, times the location of the center of gravity of the puddle, which is h/2. And so now we have two expressions, one the surface that goes like 1 of h, and the other one that goes like h. And so if we plot these two energies as a function of the height of the puddle, we have two different behavior. We have the 1 over h dependency for E sigma per unit volume. So here we are discussing energy per unit volume. And the second one associated to gravity, which is linear in h. So this is Eg by the volume. And so now if we consider the sum of these two energies, so the total energy, so this is the sum of E sigma plus Eg per unit volume. What we observe is that this shape presents a minimum, which means a thickness that minimizes the total energy. And this specific thickness that I call He is the equilibrium thickness of the puddle. And the expression if you look at what we did for E sigma and Eg, is that the thickness of equilibrium goes like the capillary length times a function of the contact angle. That goes like 2 times 1 minus cosine theta. So the conclusion that we reach about the sensitivity of puddle to wetting is that they are sensitive to wetting because their thickness is sensitive to wetting. Indeed, this equilibrium thickness is a function of the capillary length, but also of the wetting via the second factor, which write like twice 1 minus cosine theta with the square root. And so if we look at extreme values, for example, for total wetting, where theta goes to 0, then we expect the thickness of the puddle to also go to 0. This is what this formula tells us. And the radial extension by volume conservation to go to infinity. In fact, in this limit, we will have to consider the size of the molecule. So the liquid will deposit a thickness over the surface of the size of molecular size. In the opposite limit, where theta goes to pi, so this is the non-wetting limit, then the formula for the thickness tells us that He will be equal to twice the capillary length. And then the extension of the puddle will go like square root of the volume divided by pi times He. And this is our conclusion for the sensitivity of puddle, which are indeed dominated by gravity, but sensitive to wetting via this small connecting region. The interplay between gravity and surface tension is also obvious when looking at the surface of a liquid placed in contact with a vertical wall. Think of water in a glass, for instance. As we commonly observe, the liquid generally rises close to the wall until it forms a millimeter-sized meniscus. This rise could first be thought to be paradoxical, since both liquid air surface area and gravitational height increase in this deformation. This paradox is solved once we realize that for a wetting liquid, solid surface energies are decreased when solid-liquid contact is created. The shape and height of the meniscus minimize the total energy of the system that consists in both surface energies and gravitational energy. The question I want to discuss is the shape of a meniscus. Is the small region which is formed when we contact a liquid with a vertical wall, like the one you observe when you put water in your glass. And what you observe is that locally the interface is deformed. So this is the meniscus, and what we want is to describe its shape. So for this, we are going to define the distance from the wall as x, and the vertical distance z. 0 will be here. And to discuss the shape, we are going to take a point just behind the interface. We call this point A. And we are going to evaluate the pressure at this point through two different paths. So what we know is that the pressure in the air is the ambient pressure that I call P0. And if I move from this constant pressure region across the interface to reach the point A, then the pressure in A will be P0 minus the effect of the curvature that we know being proportional to surface tension and to the local curvature that I call 1 over A. In my convention, the radius of curvature, which is in fact defined as the size of the circle that tangent the meniscus here, so this is A, and I take it positive. So when I cross the interface, the pressure in the liquid will be lower due to the shape of the interface, lower by a factor gamma over the radius in A. This is the first path, so path number 1. And then I'm going to consider a second path. The second path consists of moving from the same point horizontally, so I'm still in the air, so the pressure does not change. And I reach the region far from the wall, which is not curved. So I cross the liquid in the region which is not curved, so the pressure remains P0. And then I move along an horizontal so that the pressure does not change. And I reach this location where I still have P0. And then I move up. if I move up, then I feel the effect of gravity. And so according to the second path, so path number 2 that goes this way, I have that the pressure in A following path number 2 is equal to P naught minus rho g times z in A, where z in A is the vertical location of the point A. These two expressions have to be equal, so the pressure in a point does not depend on the path that I follow. And so I conclude that the curvature 1 over A must be equal to the elevation z of A divided by the capillary length square. And this is what characterizes the shape of my meniscus. The first observation is that it's not a circle in the sense that the radius of curvature is not constant. So it is infinite where we are far from the wall. So when z equal to 0, you see that the curvature is 0, so the radius is infinite. And as we move along the meniscus, so as the elevation increases, then the curvature linearly increases. So what we found was that the shape of a meniscus, so the region that connects the liquid with the vertical wall, is given by the following relation between the local curvature, 1 over the radius of curvature, the local elevation of the interface, that is called z, and the capillary length to the square. So there are several comments that we have to do about this shape. The first one is that the meniscus is not a circle or a portion of a circle. Indeed, what we see is that the radius of curvature is not constant. So it's 0 far from the wall, and it goes to a finite value close to the wall. If we want to be more precise, there are 2 points that we can discuss. The first one is the extension of the meniscus along the x direction, which means what is the size of the region which is affected by the presence of the wall. To answer this question, what we are going to use is an expression of the curvature. So 1 over r is defined as the variation of the local angle with respect to the curvilinear location. So this is theta, and s is the distance as we move along the interface. This is the definition of the curvature. And if we are in the region which is not too steep, which is the region as we escape from the contact region, then we can approximate d theta over ds like the second derivative of z, dz square, divided by dx square. And this reduces our equation to a second order differential equation, dz square over dx square equal to z divided by lc square. And we know the solution of this equation. This solution will be equal to z naught exponential of minus x divided by LC. And this answers our question. We see that as we move in the region which is not too steep, the shape of a meniscus is an exponential with a characteristic length which is the capillary length of the interface. And so this extension is equal to the capillary length. So we will have a region of the order of 3 millimeters in the case of water that will be curved as we put water into our glass. The last point has to do with the vertical extension of the meniscus that I call h. So there exists an exact expression for h, and this expression goes like h equal to the capillary length times a function of the contact angle, which is twice 1 minus sinus theta, where theta is the angle when s equals 0. So this is our contact angle. So there are 3 cases that we can discuss about the elevation of h. The first one is when the contact angle goes to 0, so for a wetting liquid. In this case, our expression tells us that the vertical elevation will be the capillary length times square root of 2. And so this is, again, a vertical deformation that will go like the capillary length and a prefactor that depends on the contact angle. If we go to the special case, theta equal pi over 2, then we find that h equals 0, which means that we are going to contact the wall with no elevation at all. So for this special case, we could say that there is no meniscus, right? No deformation. But this no deformation limit is only observed when theta equals pi over 2. And if theta goes to the non-muting limit, so theta equals pi, then what we will find is an inverse meniscus, so something that will dive into the water. And so we will have here h equal capillary length square root of 2 with a minus sign. And these are the three limits that we can discuss with this expression. We have seen that the maximum height of a meniscus on a vertical wall is the capillary length times square root of 2. But is it possible to support a meniscus higher on a solid? The answer is yes. We have to support the liquid underneath an horizontal wall. Here, we see a meniscus made by moving a glass slide upwards from a bath of oil. With the definitions of the previous derivation, theta is here equal to 3 pi divided by 2. And the formula gives h equal to twice the capillary length. But if we try to go beyond this value, it is impossible to maintain a stable meniscus. The meniscus is the first case where surface energy pushes a liquid to climb a solid despite gravity. But this effect is modest since it takes place on typically the millimetric capillary length. A possibility to enhance markedly the rise is to confine the liquid, which can be done either in a thin gap or in a tube thinner than the capillary length. As first observed by Leonardo da Vinci and later discussed by Newton, the liquid can rise at spectacular heights. By using different glass tubes and mineral oil, Oxby showed in 1704 that the rise is inversely proportional to the tube radius. This law remains valid down to microscopic or even nanoscopic tubes, for which the rise can reach several meters. The question I want to answer is the final height that a liquid reaches when it contacts a capillary tube. So to answer this question, I will put a capillary tube of radius r in contact with the wetting liquid. And when we do the experiment, we observed that the liquid rises in the tube up to a final height that I called HE. And what I want to answer is the value of HE. To answer this question, we are going to imagine that we perturbed a little bit the position of the interface by an amount dH, and we are going to evaluate the variation of energy associated to this little displacement. I called dE the variation of energy, and dE will have two contributions. When we move the interface up, we are going to wet a little bit the side of the tube, and this will change our interfacial energies by the amount 2 pi r dH, which is the surface of the little cylinder, time the solid liquid interface that we have win by moving up, minus gamma solid vapor that we have lost. So this is the contribution of surface energies. And then we have a second contribution associated to gravity, and which will come like a mgz term, where m is the mass of liquid that has been displaced, so p r square dH times the density. So mg, and this is at the location HE. Well, what defines the equilibrium is that this variation of energy at equilibrium is exactly equal to 0. And so when we use this condition, we see that 0 has to be equal to the sum of the blue and the pink, which is 2 pi r times gamma times cosine theta, which comes with the minus sign according to Young's equation. So here theta is the contact angle here. And then I have the contribution of gravity, which comes like pi r square times the density times g times HE. Since the sum has to be 0, well, I get the expression of HE you see that HE will go like twice the capillary length squared divided by the radius of the tube times cosine theta. And this is the expression of the final height that the liquid reaches in the capillary tube. And so now we have several comments to make about this expression. So what we have found is that the final height of the liquid in the tube depends on three parameters: the capillary length to the square, the radius of the tube, and the contact angle theta. To illustrate this formula, we are going to take three different situations. The first one is the wetting limit, where theta is exactly equal to 0. In this case, when we contact the tube with the liquid, we will observe this type of situation where the final height, HE, will be twice the capillary length to the square divided by R. This formula tells us that the smaller the radius, the larger the height, which is what the experiment have shown. It also tells us that we will only observe the rise, that is, HE will be larger than the capillary meniscus of the size of the capillary length here if the tube radius is smaller than the capillary length. And finally, this formula tells us then if R goes to 0, H goes to infinity. That is, if we take tubes small enough, this effect can be huge. And if we take, for example, a tube radius of the micron size, HE will be of the order of the meter. The second situation that we can consider is the case where theta is exactly equal to pi over 2. In this case, well, nothing will happen. The formula tells us that HE will go to 0, so no rise in the tube, and we have shown that there will be no meniscus neither. So this is this very specific limit where theta equal to pi over 2. The last one is the non-wetting situation where theta equal pi, and in this case, what we will see, so the formula tells us that the HE will be negative, which means that it won't be a rise, but a sink. And the situation will go like this, where the final height, HE, will be minus twice the capillary length to the square divided by the tube radius. So these three situations illustrate what this formula tells us.
Hummingbirds feed from flowers by contacting the source of the nectar with their tongue. The tongue is roughly an open cylinder whose diameter is 600 microns, a scale at which capillary rise takes place despite the open nature of the channel. When you look carefully at this movie, showing the real tongue of a real hummingbird, you can also notice that the channel slightly pinches at the location of the meniscus. The tongue is so thin that the Laplace depression partially closes at the channel, thus enhancing the rise. This effect is more visible in the second movie, where we use an artificial tongue whose softness permits the complete closing of the tube, leading to a larger uptake of liquid.
The antagonist effects of surface tension and gravity are also observed when looking at the detachment of drops from needles, tubes, or small faucets. If we gradually feed the drop, it evolves from a quasi-sphere to a more and more elongated shapes until it detaches from the needle above some critical size, here again in millimetric range. This test is commonly used to measure surface tension, the force that prevents the liquid to fall. The question I want to address is the maximum size that a drop reaches when it detaches from a tube. If we want to answer this question, we first take a tube of radius r and then increase the volume that feeds the tube. And so the drop increases, and at one point it reaches a limit above which, if we increase a little bit, then it will detach from the tube and make drops of size Rg. And the question is to determine Rg. So if we want to answer this question, what we do is to balance the two forces that act on the drop. The first one is the weight. So the weight goes like the density of the drop times the volume of the drop times gravity. And when this force becomes equal to the force that attach the drop to the tube, which goes like twice pi times the radius of the tube times surface tension, then we will have the detachment. These relationships give us the volume that will detach. The volume that will detach will be equal to twice pi times the radius times the ratio gamma divided by Rg, which is the capillary length square. And this will be equal to the volume of the sphere that detached, which is 4/3 of pi times the radius of the drop to the cube. And so now we have the answer to our question. We find that the radius of the drop that detaches from a tube is equal to 3/2 of the radius times LC square to the power 1/3. So here we have our answer. So the radius of the drop depends on both the radius of the tube and of the capillary length of the liquid. This method of the pendant drop is used to evaluate LC. So what we have found here is the relation between R, LC, and Rg that we can rewrite as LC being equal to 2/3 of Rg cube divided by the radius of the tube to the power 1/2. And here you get a very simple method to determine the capillary length of the liquid, because in order to reach this length LC, the only thing that you need to measure is the radius of the drop that detaches and the radius of the tube that you almost impose. And by using this ratio, this gives us an evaluation with very simple means to the capillary length LC.
A cylindrical jet of liquid is naturally unstable to periodic fluctuations in radius in order to diminish the interfacial area. This leads to the fragmentation of the jet into drops. Here, the addition of 100 parts per million of a high molecular weight polymer delays the rupture of the liquid thread connecting two drops. At the bottom end of the jet, a large drop is fed by the downward moving liquid until its weight exceeds the elastic stresses generated by the stretching of the polymer molecules. Once the terminal drop is released, the end of the jet is retracted by elasticity, gobbling on its way upwards the incoming droplets, and this process repeats periodically in time.